Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
In their quest to understand the first stars and galaxies that lit up the cosmos, astronomers are still in the dark, but getting closer to enlightenment one discovery at a time. That's the incredible, inescapable conclusion from unprecedented discoveries by the James Webb Space Telescope, or JWST, the $10 billion time machine that just officially closed its first year of observations. Designed to glimpse the faint infrared glow of the universe's earliest luminous objects, Webb's vision reached back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. But its haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that defy predictions, with dozens found so far. And that makes scientists freak out. As Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We really weren't expecting this." In the weeks and months following JWST's findings of surprisingly mature early galaxies, theorists and observers scrambled to explain them. Could the bevy of anomalous big and bright early galaxies be illusory, perhaps because of flaws in analyses of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models? Or just maybe, were they the first hints that the universe is more strange and complex than even our boldest theories had ever supposed? And the Big Bang theory, was it wrong? Join us today as we dig deep into how the James Webb Space Telescope broke the universe. To understand the dilemma, let's go back to when the universe was believed to have been formed. After the Big Bang, the infant universe began cooling off. Within a few million years, the roiling plasma that filled space settled down, and electrons and protons and neutrons combined into atoms, mostly neutral hydrogen. Things were quiet and dark for a period of uncertain duration known as the Cosmic Dark Ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see called dark matter. It has exerted a powerful influence over the cosmos, especially at first. In the standard picture, cold dark matter, a term that means invisible or slow-moving particles, was flung about the cosmos indiscriminately. In some areas, its distribution was denser, and in these regions it began collapsing into clumps. Visible matter, meaning atoms clustered around the clumps of dark matter. As the atoms cooled off as well, they eventually condensed, and the first stars were born. These new sources of radiation recharged the neutral hydrogen that filled the universe during the so-called epoch of reionization. Through gravity, larger and more complex structures grew, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe as a loaf of raisin bread. It starts as a mixture of flour and water, yeast and raisins. When you combine these ingredients, the yeast begins respiring and the loaf begins to rise. The raisins within it, stand-ins for galaxies, stretch further apart from one another as the loaf expands. The Hubble telescope saw that the loaf is rising even faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy, which is represented by the Greek letter A, pronounced lambda. Plug values for A, cold dark matter, and regular matter and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda, cold dark matter, or ACDM model, matches almost all observations of the cosmos. One way to test this picture is by looking at the very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope in 1995. Over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone predicted. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, or GNZ11 if you're Canadian, a faint smudge that they dated to about 400 million years after the Big Bang. This was surprisingly early for a galaxy, but it did not cast doubt on the ACDM model, in part because the galaxy is tiny with just 1% of the Milky Way's mass, and in part because it stood alone. Astronomers needed a more powerful telescope to see whether GNZ11 or GNZ11 was an oddball or part of a larger population of puzzling early galaxies, which could help determine whether we are missing a crucial piece of the ACDM recipe. That's why James Webb Space Telescope, or JWST, was born. Renowned as the largest, most powerful observatory ever launched from Earth, the JWST was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments that were designed to uncover details of cosmic dawn never before observed. And that promise was kept. As the first discoveries were obtained, within just weeks after JWST's full operations were beyond astronomers' wildest dreams. It has seen galaxies breathtakingly close to the dawn of time, probed the atmospheres of exoplanets in unprecedented detail, and provided stunning new views of worlds in our solar system. But it's just getting started. As Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built, at stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. Webb's early revelations could rewrite the opening chapters of cosmic history, which concern not only distant epochs and faraway galaxies, but also our own existence here in the familiar Milky Way. As JWST scientist Mark McCaughrean, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm, but to break it. You just don't know how they will break it." Researchers use a version of the Doppler effect to gauge the distances of objects. This is similar to figuring out the location of an ambulance based on its siren. The siren sounds higher in pitch as it approaches and then lower as it recedes. The farther away a galaxy is, the faster it moves away from us, and so its light stretches to longer wavelengths and appears redder. The magnitude of this redshift is expressed as z, where a given value of z tells you how long an object's light must have traveled to reach us. One of the first papers on JWST data came from Naidu, the MIT astronomer, and his colleagues, whose search algorithm flagged a galaxy that seemed inexplicably bright and unaccountably distant. Naidu dubbed it Glass Z13, indicating its apparent distance at a redshift of 13, further away than anything seen before. The galaxy's redshift was later revised down to 12.4, and it was renamed Glass Z12. Other astronomers working on various sets of GWST observations were reporting redshift values from 11 to 20, including one galaxy called Cheers 1749, or CR2 Z17-1, whose light appears to have left it 13.7 billion years ago, just 220 million years after the Big Bang, barely an eye blink after the beginning of cosmic time itself. These putative detections suggested that the neat story known as ACDM might be incomplete. Somehow, galaxies grew huge right away. In the early universe, you don't expect to see massive galaxies. They haven't had time to form that many stars, and they hadn't merged together, said Chris Lovell, an astrophysicist at the University of Portsmouth in England. Indeed, in a study published in November, researchers analyzed computer simulations of universes governed by the ACDM model and found that JWST's early, bright galaxies were an order of magnitude heavier than the ones that formed concurrently in the simulations. Some astronomers and media outlets claimed that JWST was breaking cosmology, but not everyone was convinced. One problem is that ACDM's predictions aren't always clear-cut. While dark matter and dark energy are simple, visible matter has complex interactions and behaviors, and nobody knows exactly what went down in the first years after the Big Bang. Those frenetic early times must be approximated in computer simulations. The other problem is that it's hard to tell exactly how far away galaxies actually are. In the months since the first papers, the ages of some of the alleged high redshift galaxies have been reconsidered. Some were demoted to later stages of cosmic evolution because of the updated telescope calibrations. Cheers 1749, for example, is found in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago, and Naidu says it's possible the galaxy is actually part of this cluster, a nearer interloper that might be filled with dust that makes it appear more redshifted than it actually is. According to Naidu, Cheers 1749 is weird no matter how far away it is. It would be a new type of galaxy that we did not know of, a very low-mass, tiny galaxy that has somehow built up a lot of dust in it, which is something we traditionally do not expect, he said. There might just be these new types of objects that are confounding our researchers for the very distant galaxies. Everyone knew that the most definitive distance estimates would require JWST's most powerful capability. JWST not only observes starlight through photometry, or measuring brightness, but also through spectroscopy, or measuring a light's wavelengths. If a photometric observation is like a picture of a face in a crowd, then a spectroscopic observation is like a DNA test that can tell an individual's family history. Naidu and others who found large early galaxies measured redshift using brightness-derived measurements, essentially looking at faces in the crowd using a really good camera. That method is far from airtight. At a January meeting of the American Astronomical Society, astronomers quipped that maybe half of the early galaxies observed with photometry alone will turn out to actually be measured. But in early December, cosmologists announced that they had combined both methods for 4 galaxies. The JWST Advanced Deep Extragalactic Survey, or JADES, team searched for galaxies whose infrared light spectrum abruptly cuts off at a critical wavelength known as the Lyman break. This break occurs because hydrogen floating in the space between galaxies absorbs light. Because of the continuing expansion of the universe, the ever-rising raisin loaf, The light of distant galaxies is shifted, so the wavelength at that abrupt break shifts too. When a galaxy's light appears to drop off at longer wavelengths, it is more distant. Jade's identified spectra with redshifts up to 13.2, meaning the galaxy's light was emitted 13.2 billion years ago. As soon as the data was downlinked, Jade's researchers began freaking out in a shared Slack group, according to Kevin Hainline, an astronomer at the University of Arizona. He said, "It was like, oh my God, we did it, we did it," he said. "These spectra are just the beginning of what I think is going to be astronomy-changing science," he said. Brant Robertson, Jade's astronomer at the University of California, Santa Cruz, says the findings show that the early universe changed rapidly in its first billion years, with the galaxies evolving 10 times quicker than they do today. It's similar to how a hummingbird is a small creature, he said, but its heart beats so quickly that it's living kind of a different life than other creatures. The heartbeat of these galaxies is happening on a much more rapid timescale than something the size of the Milky Way. But were their hearts beating too fast for ACDM to explain? As astronomers and the public gaped at JWST images, researchers started working behind the scenes to determine whether the galaxies blinking in our view really depend upon ACDM or just help nail down the numbers we should plug into its equations. One important yet poorly understood number concerns the masses of the earliest galaxies. Cosmologists try to determine their masses in order to tell whether they match ACDM's predicted time length of galaxy growth. A galaxy's mass is derived from its brightness. But Megan Donahue, an astrophysicist at Michigan State University, says that at best the relationship between mass and brightness is an educated guess, based on assumptions gleaned from known stars and well-studied galaxies. One key assumption is that stars always form within a certain statistical range of masses called the initial mass function, or IMF. This IMF parameter is crucial for gleaning a galaxy's mass for measurements of its brightness because hot blue heavy stars produce more light, while the majority of a galaxy's mass is typically locked up in cool red small stars. But it's possible that the IMF was different in the early universe. If so, JWST's early galaxies might not be as heavy as their brightness suggests. They might be bright, but light. This possibility causes headaches because changing this basic input to the ACDM model could give you almost any answer you want. Lovell says some astronomers consider fiddling with the IMF the domain of the wicked. If we don't understand the initial mass function, then understand galaxies at high redshift is really a challenge, said Wendy Freeman, an astrophysicist at the University of Chicago. Her team is working on observations and computer simulations that will help pin down the IMF in different environments. Over the course of the fall, many experts came to suspect that tweaks to the IMF and other factors could be enough to square the very ancient galaxies lighting upon JWST's instruments with ACDM. I think it's actually more likely that we can accommodate these observations within the standard paradigm, said Rachel Somerville, an astrophysicist at the Flatiron Institute, which, like Quanta magazine, is funded by the Simmons Foundation. In that case, she said, what we learn is how fast can dark matter halos collect the gas? How fast can we make the gas cool off and get dense and make stars? Maybe that happens faster in the early universe. Maybe the gas is denser. Maybe somehow it is flowing in faster. I think we're still learning about those processes. Somerville also studies the possibility that black holes interfered with the baby cosmos. Astronomers have noticed a few glowing supermassive black holes at a redshift of 6 or 7, about 1 billion years after the Big Bang. It is hard to conceive of how, by that time, stars could have formed, died, and then collapsed into black holes that ate everything surrounding them and began spewing radiation. But if there are black holes inside the putative early galaxies, That could explain why the galaxies seemed so bright, even if they're not actually very massive, Somerville said. Confirmation that ACDM can accommodate at least some of JWST's early galaxies arrived the day before Christmas. Astronomers led by Benjamin Keller at the University of Memphis checked a handful of major supercomputer simulations of ACDM universes and found that the simulations could produce galaxies as heavy as the 4 that were spectroscopically studied by the JADES team. These 4 are notably smaller and dimmer than other purported early galaxies, such as Glass Z12. In the team's analysis, all the simulations yielded galaxies the size of the JADES findings at a redshift of 10. One simulation could create such galaxies at a redshift of 13, the same as what JADES saw, and 2 others could build the galaxies at an even higher redshift. None of the JADES galaxies was in tension with the current ACDM paradigm, Keller and colleagues reported on the preprint server arcs4.org on December the 24th. Though they lacked the heft to break the prevailing cosmological model, the JADES galaxies have other special characteristics. Heinlein said their stars seem unpolluted by metals from previously exploded stars. This could mean they are population 3 stars, the avidly sought first generation of stars to ever ignite, and that they may be contributing to the reionization of the universe. If this is true, then JWST has already peered back to the mysterious period when the universe was set on its present course. Despite the big picture findings stuck, the early universe was somehow bold and brash and remarkably luminous. The objects we are finding are as massive or larger than the Milky Way, which is astounding, said Leah, who co-published a paper last week that identified 6 enormous galaxies that existed just 500 to 700 million years after the Big Bang. Frankly, such early galaxies are not in themselves surprising. Astronomers expected that the first star clusters sprung up shortly after the universe moved out of the so-called Dark Ages, the first 400 million years of its existence, when only a thick fog of hydrogen atoms permeated space. But the galaxies found in the Webb images appeared shockingly big, and the stars in them too old. One of these galaxies may have a mass of 100 billion times of that of the Sun. Our own galaxy similarly contains many billions of stars, but it has had 13 billion years to reach its size. It's bananas, said Erica Nelson, assistant professor of astrophysics at CU Boulder, and one of the authors of the study. In a press release, she said, "You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form. It's just crazy that these things seem to have existed that early." Or as Leisha said, "We've been informally calling these objects universe breakers, and they have been living up to their names so far." As a result, for a brief moment, this new reality seemed to threaten astronomers' fundamental understanding of the entire cosmos. If the starting point looked like that, could the standard model of cosmology, our strongest theory about the origins and composition of the universe, the one that didn't account for what Webb found, be wrong? But astronomers now believe that the theory can accommodate the new telescope's surprises. Recent computer simulations guided by the standard model have shown that the universe could indeed have created some of the galaxies that Webb has found. While on the face of it, the data don't seem consistent with cosmological models, I think what we're going to find is it's not cosmology that's the problem, but really what we understand about how galaxies formed, Leisha said. The possible explanations for how astronomers got it wrong are plentiful. Perhaps early stars formed far more efficiently than we thought, through mechanisms that scientists hadn't considered before. Alison Kirkpatrick, an astronomer at the University of Kansas who studies galaxy evolution, wonders whether cosmic dust in these galaxies could be playing tricks on Webb, making stars appear older than they actually are, and maybe cosmic dust was just different back then. Ivo Labe, an astronomer at Swinburne University of Technology, suspects that black holes could play a role. They are among the most luminous objects in the universe when they're feeding on cosmic matter, which glows as it gets sucked in. If you dump a lot of gas into a black hole, it will start to outshine the entire galaxy, Labe said. Such black holes could make early galaxies appear brighter, more star-filled. But none of these possibilities will undo the fact that the first island universes are not what we expected. Even accounting for some new weird phenomena, everything's too big, and it's too big too soon, Labe said. Investing these questions will require more Webb observations, particularly the kind that yield more detailed measurements of starlight, known again as spectroscopy. Astronomers need more to confirm that the most unusual galaxies they've found are the real deal. And if they really are as old and big as they seem, understanding their composition will help astronomers suss out the conditions in which they formed. Researchers are in the thick of it now, with full spectroscopic data expected to come in this spring. The effort verges on soul-searching. Primordial starlight has never been so in demand, and astronomers and theorists, those who observe cosmic wonders and those who explain them respectively, don't know exactly what they'll find out once they're finished. It's probably going to be something like 5 years until we've totally settled into our new universe theory that we've gotten from JWST, Ren Suss, an astronomer at UC Santa Cruz and Stanford, said. In one sense, these new discoveries have injected drama, even anxiety, into a field that was actually quite stable. But as Nelson shared, it's incredible how the universe is just so much weirder than we thought it was. It's the beginning of the universe, so it's really fun to think about this kind of stuff. It could be said that the James Webb's first year of observations, Cycle 1, ended spectacularly. Astronomers are amazed and blown away by what Webb has achieved so far. But more interesting results may occur in its second year of science, or Cycle 2. Like Cycle 1, the competition was fierce, and while there were plenty of winners and some incredible science set to be conducted, there were many more who missed out on JWST's Cycle 2, which starts this month. As Nancy Levinson, interim director of the Space Telescope Science Institute, or STSCI, in Maryland, which runs JWST, said, there was an extraordinary response from the science community. In total, astronomers submitted about 1,600 proposals to STSI for observing time on the NASA-led JWST, but only 249 were actually selected, meaning that JWST has an oversubscription of nearly 7-to-1, similar to that from the Hubble Space Telescope. To minimize the chance of bias, the process of selecting JWST's programs is completely anonymous, with hundreds of astronomers from multiple subfields involved in the decision process. That said, there were clear winners and clear losers. Some astronomers, such as Nathan Adams of the University of Manchester in England, put forward multiple proposals that were ultimately rejected. We had 4 proposals, he said, and none of them got time, Adams says. Obviously, we're a bit disappointed. Others, such as Marianne Leimbach of Texas A&M University, were much more successful. Leimbach had 3 proposals approved. We're excited about the time we got, she said. Leimbach's proposals are focused on white dwarfs, the remnant Earth-sized cores left behind after stars such as our Sun swell into red giants and expel their outer layers. After this dramatic event, it's thought these stellar corpses can still harbor intact planets, potentially offering us the chance to study them and learn more about the fate likely to befall Earth in 5 billion years when our Sun enters its red giant phase. Leimbach will attempt to confirm 2 suspected white dwarf worlds, but will also search for up to a half-dozen more elsewhere in the sky. JWST can see if any of these nearby white dwarfs look brighter than they should be, she said. If they do, that could be an indicator there's a planet there. JWST is really the only observatory capable of confirming them, she said. A dominant area of JWST's Cycle 1, which had about 1,200 proposals, was hunting for the earliest known galaxies in the universe, which were formed just a few 100 million years after the Big Bang. The same is true for Cycle 2, with both galaxies and exoplanets getting the most telescope time. An accepted proposal from Daniel Einstein of Harvard University is hoping to push JWST to its limits by hunting for galaxies perhaps up to just 200 million years post-Big Bang. Distances far away galaxies are measured in redshift. The degree to which light we see from a galaxy has been shifted to the red end of the spectrum by the universe's expansion. Einstein will hunt for galaxies beyond redshift 15, farther than any others conclusively seen so far. We don't yet have a convincing case of a galaxy beyond redshift 15, he says. It's really exciting to be able to continue the search that started in this first year. Rohan Naidu of the Massachusetts Institute of Technology will also be scouring the distant universe, but not for those highest redshift galaxies. Instead, his program, which he co-leads with Jarrett Matthey of the Swiss Federal Institute of Technology in Zurich, or ETH Zurich, will be using a giant cluster of galaxies called Abell 2744 to gravitationally magnify the light of some smaller objects up to 750 million years after the Big Bang. The goal is to look for clumps of primordial gas which could contain clusters of population 3 stars, the first stellar generation thought to have lit up the universe. These long theorized objects have yet to be directly seen, but are expected to be composed almost entirely of pure hydrogen and helium, which should allow them to be enormous, each weighing in hundreds of times heavier than our Sun. We're really pushing JWST to the hilt, Naidu says. We'll get back some very promising regions that might be hosting these clusters. A key target of interest for JWST's Cycle 1 was the TRAPPIST-1 system, an arrangement of 7 Earth-sized worlds, some of which might be habitable, around a red dwarf star about 40 light-years from Earth. While 3 TRAPPIST-1 programs were selected in Cycle 1, however, only one has been selected this time, led by Michael Gillian of the University of Liège in Belgium. He will hunt for atmospheres on TRAPPIST-1b and c, the 2 innermost planets of the system. Earlier studies of TRAPPIST-1b suggest it has no atmosphere, but Gillian says his technique, measuring the temperature difference between the day and night side of the planet, will tell us more for sure. That could have important implications for TRAPPIST-1's other more temperate worlds that might conceivably support life. If we can demonstrate that one of these 2 planets has an atmosphere, we will be in a very good position to ask for an ambitious program on JWST to dig into other planets, he says. Closer to home, Christopher Glein of the Southwest Research Institute, or SWRI, in Texas, will use JWST to probe Saturn's moon Enceladus, which may harbor a habitable ocean beneath its icy surface. Observation from NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, showed that the moon occasionally ejects water from its oceans via a plume at its south pole. While no spacecraft currently orbits Saturn, JWST is the next best thing. Incredibly, it will be able to look for evidence of ocean chemistry on the surface of Enceladus, Glein says. It will even be sensitive to certain substances, such as ammonia and various organic molecules, that could tell scientists about the habitability of the moon's hidden ocean. In 2040, Enceladus' south pole will enter a long winter of darkness that will last until 2055, making a potential future landing there to hunt for life difficult. Glein, however, is hoping to show with JWST that the moon's polar plume is depositing frozen sea spray all across the surface, perhaps all the way up to the sunlit equator, where a landing could be more feasible. JWST can act as a bridge between the Cassini era and a lander on Enceladus, he says. Not all areas of research were so lucky. David Kipling of Columbia University submitted 2 proposals to use JWST to hunt for moons orbiting exoplanets, known as exomoons. JWST is the first machine humanity has ever built that is actually capable of doing this experiment, Kipling says. But both proposals were rejected. We're definitely disappointed, he says. We really felt like this was a slam dunk argument. JWST should be able to find exomoons down to the size of Europa, Kipling says, but even if it can't, the results would be pretty profound. A failure to turn up an expected population of exomoons would mean the models we use in our solar system aren't universal, he says, and could be a clue that our local abundance of lunar satellites is a bizarre deviation from cosmic norms. Time is of the essence, considering JWST is the only telescope now, or for the foreseeable future, that can look for exomoons. JWST could last 10 years, maybe longer, Kipling notes. If we never look for exomoons with it, we really would regret it. That would be such a shame, he said. Levinson knows that there will be some disappointments from the programs that were not selected. There are a lot of great ideas that we are just not going to be able to observe during this cycle, she says. For those that missed out, the deadline to try again and apply for Cycle 3 is October. We have to keep trying, Kipling says. JWST is not going to be there forever. For those lucky few that did make the cut, there are scientific riches to be had. There's this whole range of science that JWST is just great for, says Levinson. We're definitely not done yet.
Out in the depths of space, the James Webb Space Telescope is already revolutionizing what we thought about the universe. For James Webb, the hits just keep coming, one riveting image after another, from the far reaches of the universe to planets right here in our own solar system. We got our first taste a year ago, and the images did not disappoint. The Carina Nebula, Stephan's Quintet, and, spectacularly, this so-called deep field image showing thousands of galaxies stretching into the distant universe. But perhaps the most amazing thing revealed by James Webb is that the furthest you look back in time, there were already huge, mature, and fully formed galaxies that shouldn't exist. Some of them even might be older than the universe, and scientists call them universe breakers. Nobody expected them. They were not supposed to be there. And now, nobody can explain how they had formed. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb's shocking discoveries could shatter our leading explanation for how the universe began. Originally, the Big Bang was a simple idea that grew out of 3 facts, all put together. In Einstein's general theory of relativity, a universe filled with any uniform distribution of matter and/or energy will not be stable in a static configuration. The fabric of space in that universe must either contract or expand. Observationally, there are spirals and ellipticals in the sky, and they lie well beyond the Milky Way. Their distances can be measured. Also observationally, the light from these spirals and ellipticals appears to be shifted, with more distant objects exhibiting a greater redshift in direct proportion to their distance, consistent with an expanding universe. By combining these 3 facts, we'd conclude that the universe, if it's expanding and becoming less dense today, must have been smaller and denser in the past. We can extrapolate this back farther and farther, to even very early times if we like, and recognize that our modern universe must have emerged from a denser, smaller, more uniform state in the very distant past. The first person to synthesize this information together was Georges Lemaitre, who did it in 1927, although others would independently come to the same conclusion, including Howard Robertson in 1928, Edwin Hubble in 1929, and Arthur Walker a few years later. Over time, we were able to derive many more consequences from the Big Bang, including that the early state must have been hotter as well as denser, and that as the universe expands, it also cools. This allowed us to predict that there would be a leftover bath of low-energy radiation with a blackbody spectrum in all directions, arising from when the universe cooled through the threshold that enabled it to form neutral atoms. That the universe would have, at even earlier times, been hot and dense enough to initiate nuclear fusion reactions before any stars could form, leaving us with an initial abundance of elements other than hydrogen among the pristine set of atoms that the universe begins with. And that, once neutral atoms form, the universe begins gravitating to form structure in the universe. Stars, star clusters, clouds of gas, galaxies, galaxy clusters, and eventually the great cosmic web, filled with filaments and voids. All of these aspects of the Big Bang have been verified and validated, ruling out a great many alternatives that cannot reproduce these successes. Today, there are 3 additional ingredients that we've learned, and tested and verified, are also present in the universe. Dark matter, which clumps and gravitates but doesn't collide with normal matter or photons. Dark energy, which behaves as a form of energy inherent to space itself. And cosmic inflation, which limits how far back into the past we can extrapolate the hot Big Bang before matter and radiation no longer dominated the energy contents of the universe. This picture enables us to do something remarkable. Inflation allows us to describe the initial conditions of the universe at the start of the hot Big Bang. How hot and dense it was, what the initial spectrum of density imperfections were, including that were all adiabatic Gaussian random fluctuations, and what the magnitude of these fluctuations were on all cosmic scales. Our knowledge of the Standard Model, plus the additions of dark matter and dark energy, enable us to state what the various types, energies, and abundances of all the different species of energy were at all cosmic times. From that starting point, our knowledge of the laws and interactions that govern the universe enables us to time-evolve these initial conditions from the start of the hot Big Bang all the way up through the present day. We can make both theoretical predictions and perform numerical simulations that tell us what should arise and when, in an expanding universe that begins with a hot Big Bang and the properties we've determined it ought to have. However, despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. And with the recent addition of the James Webb Space Telescope to the arsenal of tools astronomers have, James Webb continue fuel doubts about the Big Bang theory, as its early universe observations cannot be explained by current cosmological models. The James Webb has literally gone further than any similar instruments used by NASA before. As Matt Greenhouse, who has served on the James Webb's senior staff as a project scientist, the James Webb Space Telescope has given humanity its first high-definition view of the infrared universe. Thanks to Webb's unprecedented capabilities, for the first time, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Prior to James Webb, we had one confirmed galaxy GNZ11 at an age of about 400 million years after the Big Bang, and only one other galaxy candidate, possibly at an age of around 330 million years after the Big Bang. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day, more than 1 year after James Webb began science operations, and the story has changed dramatically. We have over 100 galaxy candidates from James Webb that take us back to the first 400 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. GNZ11 already is now only the 5th most distant galaxy known, and it's fully expected that over the next months, not only will the current cosmic record for distance, jot as GSZ13-0, from a time just 320 million years after the Big Bang, be broken, but that at least dozens of new ultra-early, ultra-distant galaxies will soon be confirmed. Many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. For example, they appear to be very massive, very bright, very rich in heavy elements, very actively forming new stars, and very rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling, because we believe we understand how gas infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Therefore, when we look at these very early galaxies, we do get the impression that something is amiss. It is clear that galaxies captured by James Webb are so massive that they should not be possible under current cosmological theory. Thus, Big Bang astronomers are now stunned and surprised because, according to the Big Bang theory, those galaxies shouldn't be there. There should have been only primordial dust from which they assume that stars and galaxies originated after a primeval explosion. The James Webb Telescope is challenging the Big Bang theory held by most scientists, and it is causing consternation in the scientific community, at least among those scientists who believe in the Big Bang origin of the universe. Big Bang scientists believe that the expansion of galaxies in the universe came from a singularity that exploded billions of years ago. Yes, some galaxies may be expanding, moving further away, what is called red shift. But this is not necessarily the case with the entire universe, and not even all scientists, including evolutionary scientists, interpret red shift in our universe as meaning galaxies are expanding, or that there was a primeval Big Bang from which the universe sprung. It has been said that publishers of prestigious science journals refuse to publish papers and research from scientists who refute the Big Bang theory. Canadian physicist and scientist David Rowland asserts in his internet article, "The Big Bang never happened, several scientific contradictions to the Big Bang that have been conveniently glossed over or ignored in order to support the much-cherished Big Bang theory held by the majority of scientists." These scientists have had to resort to the internet to publish their scientific arguments refuting the Big Bang theory. Rowland says that the red shift in actuality is not a measurement of velocity, of showing that galaxies are expanding and moving away, but only a measurement of temperature and distance. He says that Big Bang scientists initially confused the red shift from galaxies with the Doppler effect, and this confusion led these earlier scientists to believe that the universe was expanding. Rowland points out that the light from galaxies naturally attenuates over long distances, and that this attenuation had been wrongly interpreted by early scientists as evidence that galaxies in our universe must be expanding. Once this belief had set in early on, it continued to be taught and held by the majority of scientists to this day. Even the famed astronomer Edwin Hubble, after whom NASA named its famed telescope, and who discovered the redshift, expressed doubts about interpreting the redshift as evidence that galaxies are expanding. Hubble believed there could be other reasons for the redshift. Hubble refused to believe that the redshift was proof of galaxies expanding. Even if there was a past expansion of galaxies, this does not mean that the galaxies at present are expanding. We can only see the past from telescopes, not the present. Interestingly, the Bible teaches that the heavens at one time expanded. Various passages in the Bible speak of God stretching out the heavens. If the Big Bang really occurred, there would have been a uniform distribution of gases in space. This uniform distribution of gases throughout the universe would have made sure that the gases didn't have enough gravitational attraction to form into planets and stars. Big Bang scientists must assume the existence of dark matter in the universe to provide enough gravitational force for stars and galaxies to form. However, there still is no scientific proof for the existence of dark matter. In fact, the hypothesis of the existence of dark matter has been increasingly discredited by science. Big Bang scientists believe that dark matter can be the only gravitational explanation for how galaxies behave. However, other scientists have successfully shown an alternative explanation to dark matter known as MOND, which stands for Modified Newtonian Dynamics. In other words, it is not necessary to believe that 80% of the universe must be made up of dark matter in order to explain certain behavior and movement of galaxies. The late creationist and scientist Dr. Duane T. Gish said, "The galactic structures discovered during the past few years, however, are so massive that even if cold dark matter did exist, it could not account for their formation." Furthermore, an explosion cannot explain the precise and orderly orbits and courses of thousands of billions of stars in thousands of billions of galaxies. Gravity may explain how that order is maintained, but mere gravity cannot explain the origin of that order. The disorder in the universe can be explained because of chance and random processes, but the order can only be rationally explained because of an intelligent power. Some evolutionary astronomers believe that trillions of stars crashed into each other, leaving surviving stars to find precise, orderly orbits in space. Not only is this irrational, but if there was such a mass collision of stars, then there would be a supermass residue of gas clouds in space to support this hypothesis. The present level of residue of gas clouds and dust in space doesn't support the magnitude of star deaths required for such a hypothesis. It's more rational to believe that stars die and decay into gas clouds and dust instead of believing that gas clouds and dust evolve into stars, as evolutionary astronomers teach. Evolutionary astronomers only assume that gas clouds and dust in the so-called pillars of creation are birthplaces for stars. This assumption is conveniently passed on as fact in textbooks and media. In another remarkable effort to explain Webb observations, the scientist proposed a hybrid model that combines aspects of the tired light model and a cosmological model based on evolving coupling constants. This new model suggests a longer galaxy formation time, allowing for the formation of well-evolved early galaxies. However, further research and scrutiny are required to determine if this model can provide a satisfactory explanation for all the observations in cosmology. On the other hand, the need for a new cosmology is not unprecedented in the scientific community. Mixing models to explain new observations has been done in the past, such as Albert Einstein's explanation of the particle-like and wave-like nature of light. Similarly, estimating the age of the universe based on the age of stars in globular clusters has also been used as an alternative method. In conclusion, the discrepancies between observations and the standard model of cosmology have prompted the proposal of a new model that suggests a longer age for the universe. While this new model shows promise, further research is needed to determine its validity and if it can provide a comprehensive explanation for all cosmological observations. And as a worth note, the eagle eye of James Webb has just discovered two of the most distant galaxies ever seen, supporting the basic picture of galaxy formation as described by the Big Bang theory. The discovery was made possible thanks to a huge helping hand from a massive gravitational lens in the form of the galaxy cluster known as Abell 2744, nicknamed Pandora's Cluster, which is located about 3.5 billion light-years away from us. The immense gravity of the cluster warps the very fabric of space-time sufficiently to magnify the light of more faraway galaxies. Using the James Webb Space Telescope to search for early galaxies magnified by this cosmic lens, Bingji Wang of the Penn State Eberly College of Science and member of the James Webb Space Telescope Ultra-Deep Near-Infrared Spectrometer and Near-Infrared Camera observations before the epoch of Rionization or Uncover team discovered two of the highest redshift galaxies ever seen. Cosmological redshift, as told, is the stretching of light wavelengths, provoked by the continuous expansion of the universe. The more distant a galaxy is, the more the universe had expanded while that galaxy's light traveled across space to reach us, and therefore, the more the wavelengths of that light are stretched. As wavelengths get stretched out in this manner, they go from tighter, bluish ones to redder ones, eventually falling into the invisible infrared region of the electromagnetic spectrum. Galaxies that existed just between 300 and 400 million years after the Big Bang have had their light stretched into those infrared wavelengths that can't be seen by humans, but can indeed be detected by the Webb's near-infrared camera and near-infrared spectrometer instruments. Wang and her team were able to identify the lensed images of two high redshift galaxies. One, designated Uncover Z13, Z is shorthand for redshift, has a redshift of 13.079, confirming it to be the second most distant galaxy known. The most distant confirmed galaxy is Jade's GSZ 13.0, which was also discovered by the James Webb in 2022 and has a redshift of 13.2. We see Uncover Z13 as it existed just 330 million years after the Big Bang. The other galaxy recently discovered, Uncover Z12, has a redshift of 12,393, placing it in fourth place in the all-time list of most distant galaxies. We see this realm as it was just 350 million years after the Big Bang. What marks the two Uncover galaxies out as different is their appearance. Other galaxies seen at similarly high redshifts seem to be point-like, indicating they are very small, just a few hundreds of light-years across. The Uncover galaxies, on the other hand, have structure. Previously discovered galaxies at these distances appear as a dot in our images, Wang said in a statement, but one of ours appears elongated, almost like a peanut, and the other looks like a fluffy ball. These galaxies are also bigger, with Uncover Z12 sporting an edge-on disk about 2,000 light-years across, which is 6 times larger than other galaxies seen in this era. It is unclear if the difference in size is due to how the stars formed or what happened to them after they formed, but the diversity in the galaxy properties is really interesting, said Wang. These early galaxies are expected to have formed out of similar materials, but already they are showing signs of being very different than one another. Although the dichotomy in galaxy properties, even at this early stage in the universe, is eye-opening, both of the newfound realms have general characteristics that are strongly supportive of the Big Bang model. This model describes how, in the aftermath of our universe's creation, galaxies began life small before growing rapidly through mergers with other galaxies and gas clouds. This growth, in turn, spurred more star formation, which ultimately increased the abundance and variety of elements contained within the young galaxies, introducing substances to them that are heavier than hydrogen and helium. The galaxies uncovered by Uncover, if you'll pardon the pun, are young, small, have a low abundance of heavy elements, and are actively forming stars, all of which supports the whole paradigm of the Big Bang theory, Joel Leja, who is an assistant professor of astronomy and astrophysics at Penn State University and a co-researcher on Wang's team, said in the statement. Interestingly, the Webb telescope has the ability to see even higher redshift galaxies than Uncover Z13 and S12, meaning they'd be even younger, but it didn't detect any being lensed by the Pandora cluster. As Leia said, that could mean that galaxies just didn't form before that time and that we're not going to find anything farther away. Or it could mean we didn't get lucky enough with our small window. Astronomers will keep looking, using a multitude of lensing clusters to open up new windows into the deep universe in search of some of the first galaxies.
Something is awry in our expanding cosmos. Nearly a century ago, the astronomer Edwin Hubble discovered the balloon-like inflation of the universe and the accelerating rush of all galaxies away from each other. Following that expansion backward in time led to our current best understanding of how everything began: the Big Bang. But over the past decade, an alarming hole has been growing in this picture. Depending on where astronomers look, the rate of the universe's expansion, a value called the Hubble constant, varies significantly. Now, more than 2 years after its launch, the James Webb Space Telescope has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. According to Adam Rees, a professor of astronomy at Johns Hopkins University, who led the team that made the new James Webb measurements, It's a disagreement that has to make us wonder if we really do understand the composition of the universe and the physics of the universe. On this, many cosmologists can agree. It started with a bang. Then, in an instant, the young cosmos was formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence, only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma mire should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched space-time, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, the standard story goes, ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density and therefore its expansion rate decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of space-time. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped, while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter or LCDM model of cosmology, which maps the growth of the cosmos and predicts its end. With matter eventually spread so thin, it experiences a heat death called the Big Freeze. Many of the model's predictions have been proven to be highly accurate, but here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary, atomic matter, 25% cold, dark matter, and 70% dark energy. The embarrassing fact is, we don't understand the last two of them. But an even greater threat to the LCDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. And methods that peer into the early universe show it expanding significantly faster than LCDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Rees said, the only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little bit more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, or CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump. As the universe exploded outward, this soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant, or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will retreat from us, and us from it, at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second, and continues to grow exponentially there onward. If a galaxy is any further than 4,475 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables, dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness, and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant, standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. Wendy Friedman, an astrophysicist at the University of Chicago, said, "To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 kilometers per second per megaparsec when compared to the Planck measurement. Yet Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So, when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meter wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 meter wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC4 258 with bright Type 1 supernovas, another standard candle because they all burst at the same absolute luminosity, in remote galaxies, Rees and his colleagues arrived at a nearly identical result: 73 kilometers per second per megaparsec, including one made by Friedman with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch, red giant stars, and another with light bent by the gravity of massive galaxies, came back with respective results of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using the bending of light also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Ryan Keeley, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension, the CMB temperature is measured at the level of 1% precision, and the Cepheid distance ladder measurement is getting close to 1%. So a difference of 7 kilometers per second, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmologists into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, or KITP, in California, only caused more frustration. As David Gross, former director of the KIT and a Nobel laureate, said at the conference, "We wouldn't call it a tension or problem, but rather a crisis." But how things can be fixed is unclear. Rees is pursuing a tweak to the LCDM model that assumes dark energy isn't constant, but instead evolves across the life of the cosmos, according to unknown physics. However, Keely's research contradicts this. He and his colleagues found that the expansion rates matched the predictions of LCDM model all the way back to the CMB. So, if the model needs fixing anywhere, it's most likely in the very early universe. It could be possible to add some extra dark energy before the emergence of the CMB, giving some additional oomph to the universe's expansion that needn't make it break from the standard model. Another group of astronomers is convinced that the tension alongside the observation that the Milky Way resides inside an underdense supervoid means that LCDM and dark matter must be thrown out altogether. What should replace it, according to Pavel Krupa, a professor of astrophysics at the University of Bonn, is a theory called modified Newtonian dynamics, or MOND for short. The theory proposes that for gravitational pulls 10 trillion times smaller than those felt on Earth's surface, such as the tugs felt between distant galaxies, Newton's laws break down and must be replaced by other equations. Other astronomers say that their own calculations nix the MOND claims, yet Krupa insists that cosmologists looking to tweak the standard cosmological model are basically adding additional complications to an already very messy and complicated theory. According to Krupa, what we are experiencing and witnessing is an essential breakdown of science. A more optimistic thought, it's possible that the standard model just needs a tweak, or maybe dark matter and dark energy are the modern-day equivalent of epicycles, the small circles ancient Greek astronomers used to model planets orbiting Earth. The orbits of planets were described very accurately by epicycles, Lahav said. It was a good model. It fitted the data. But once astronomers placed the sun in the center of the solar system in newer models, epicycles eventually became irrelevant. If we want to go philosophical, maybe that's what's going on. But maybe also there is dark matter and dark energy, and it's just not been discovered yet. Cosmologists are looking for answers in a number of places. CMB experiments, such as the CMB S4 project at the South Pole and the Simons Observatory in Chile, are searching for clues in ultra-precise measurements of the early universe's radiation. Others will look to the dark matter maps produced by European Space Agency's Euclid Space Telescope, or to the future dark energy survey conducted by the Dark Energy Spectroscopic Instrument. Although it now may seem less likely, it's also still possible the Hubble tension could be resolved by figuring out some unseen systematic flaw hiding inside current measurements. And for scientists like Friedman, such a solution, or possibly further riddles, will come from James Webb. Her team is using the telescope's powerful eye to make ultra-detailed measurements of Cepheid variables, tip of the red giant branch stars, and a type of carbon star called JAG-B stars all-at-once distance. Once the necessary data is collected, we'll see how well they agree, and that will give us a sense of an overall systematic answer. In other words, one day, the James Webb Telescope could settle a long-standing debate. Just hope that day comes soon. After all, as you see, while it would seem that scientists and astronomers know an awful lot about the universe, we are nowhere near knowing everything there is to know. There are still many unsolved mysteries surrounding our universe. Here are some of the most pressing issues occupying the finest astronomical minds of the 21st century, and they expect James Webb to shed light on the mysteries of our vast universe. How supermassive black holes merge. When a black hole smashes into another black hole, it sends shock waves rippling out through space itself, gravitational waves. Yet so far, the mergers we've seen have come from so-called stellar mass black holes, those with masses a few tens of times the mass of our sun. That's tiny compared to a supermassive black hole, which can tip the scales at billions of solar masses. There's a supermassive black hole in the center of every major galaxy, and galaxies also collide. So what happens to the two black holes at their hearts? You'd think that they'd merge too, but there's a problem. To spiral inwards, the black holes need to lose energy, which they do by shedding heat to surrounding gas, dust, and stars. Yet when they get within a parsec of each other, there's no longer enough stuff to lose energy to. This final parsec problem means the supermassive black holes should remain orbiting each other and never actually merge. However, recent evidence from the nanograv experiment suggests that the universe is humming with gravitational waves from supermassive black hole mergers. The data from this hum might give astronomers the clues they need to finally unpick this problem. 2. What the universe actually looks like. Look at the large-scale structure of the universe today, and countless galaxies are strung out on endless filaments in a cosmic web. It seems that tiny variations in density in the very early universe acted as seeds from which this structure eventually blossomed. Over dense regions drew in more and more material to create galaxy-filled superclusters and leave behind supervoids. Except the Big Bang Theory says that the early universe should have been completely smooth. How come it had tiny imperfections of just a few parts in 100,000, but which created the universe as we see it today? One explanation is a modification to the Big Bang called inflation, which states what happened in the first few seconds of the universe. It argues that the universe underwent a period of super rapid expansion in the first minuscule fraction of a second. The cosmos went from considerably smaller than an atom to about the size of a grapefruit in a trillionth of a trillionth of a trillionth of a second. Before this, the universe was so small that it was dominated by minute quantum variations. The ensuing explosion in size blew up those variations. It's worth saying that currently there's no evidence that inflation really happened, although it does help solve other problems with the Big Bang too. Nor do we know the universe's true size. Astronomers speak about the observable universe, a spherical region 13.8 billion light-years in all directions where light has had time to reach us since the Big Bang. However, there could well be things beyond this cosmic horizon that are so far away the light hasn't arrived at Earth yet. This also makes it difficult to determine what shape the universe is. Astronomers currently believe the 4D fabric of space-time is flat, but it could simply be that inflation has smoothed out the billions of light-years we can see. And beyond that, the universe is actually curved. One thing we don't know about the universe is its shape. 3. What gravity really is. While we know what gravity does, it's unclear how it does it. Our current best theory of gravity is Einstein's general theory of relativity. It says that massive objects like the sun warp space-time, the fabric of the universe, around them. Earth is then caught in the distortion that the sun makes, which is why we orbit. Except this isn't how physicists treat any of the three other fundamental forces. They are all carried by particles called bosons. Magnets attract each other, for example, by exchanging bosons called photons. So the hunt is on for the graviton, a so far hypothetical particle that would be responsible for gravity. 4. What happens inside a black hole? One of the most asked questions about black holes is, what would happen if you fell into a black hole? Wander too close to the horizon of a black hole, and the extreme difference in gravity between your head and your feet would rip you apart into lengths of human spaghetti. But where does that pasta eventually end up? Our best theory of black holes is Einstein's general theory of relativity. It says that inside a black hole space becomes increasingly concentrated into an ever smaller volume. In fact, at the very bottom space is crushed into an infinitely small speck called a singularity. However, a singularity is likely to be a placeholder for our ignorance. The curvature of space becomes infinite, and the singularity's density becomes undefined. In other words, the laws of physics suddenly lose their predictive powers. The elephant in the room is quantum physics. If you squeeze space down into a volume smaller than an atom, then quantum physics probably has something to say on what happens. However, despite many valiant attempts, physicists have yet to combine general relativity and quantum physics in a satisfactory way. If we one day create a so-called theory of everything, we may find out what we need to replace a singularity with. 5. What dark matter is. There's something about galaxies that just doesn't make sense. They're rotating far too fast. So fast that their outer stars should fly off into space, but that's not happening. Instead, astronomers suspect that galaxies contain an invisible gravitational glue called dark matter that helps to keep hold of those stars. But what is dark matter made of? This is one of the most significant things we don't know about the universe, in that it's a key unanswered question. For decades, the leading idea has been something called weakly interacting massive particles, or WIMPs. Except physicists have gone to great lengths and performed extensive and exhaustive searches for them, and they haven't seen a single one. And so they're starting to look seriously at other options. Other candidates include that dark matter is caused by the gravity of tiny black holes formed shortly after the Big Bang, known as primordial black holes. Or dark matter could be particles called axions, which physicists conjured up to solve a problem in particle physics. There's a chance that dark matter isn't actually a physical substance at all, but an illusion instead. This is the premise behind a theory known as MOND. It says that the missing gravity is actually due to the fact that gravity works differently on the scale of galaxies, and we've been misinterpreting the situation. 6. Which way up galaxies form. There are hundreds of billions, perhaps even trillions, of galaxies in the modern universe. But where did all these star cities come from? There appear to be two ways to make a galaxy. You could start small with individual stars and minor star clusters. Over time, gravity, added by the glue of dark matter, could then bind lots of these together to form the conglomerations we call galaxies. This is a so-called bottom-up approach. The alternative is top-down, where huge structures form early in the universe's history, only to fragment into galaxies as the cosmos aged. The James Webb Space Telescope is currently wowing astronomers with insights into the early universe. It has seen fully fledged galaxies just 400 million years after the Big Bang, and even some that appear to be merging. So that seems to favor the bottom-up approach, but it needn't be a binary situation. It may be possible for some galaxies to form bottom-up, while others formed top-down. Huge upcoming galaxy surveys like those with the Vera Rubin Observatory in Chile could help us to know more. Plus, the Webb telescope is only just getting started. 7. How the universe will end. Astronomers used to think that the gravity of everything in the universe would eventually pull the cosmos back in on itself in a reversal of the Big Bang dubbed the Big Crunch. However, that was before they discovered that the expansion of the universe is accelerating due to a shadowy entity known as dark energy. If it continues to accelerate, all structures in the universe, even atoms, will be torn apart within 22 billion years in a so-called Big Rip. A more sedate expansion would lead to a big freeze instead, where the expansion of the universe causes it to cool so much that stars cannot shine, and the universe eventually settles into a uniform temperature. In the vast expanse of the cosmos, where mysteries abound and the unknown stretches endlessly, the James Webb Telescope, JWT, stands as a beacon of human curiosity and technological prowess. This groundbreaking instrument, heralded as the most advanced space observatory ever created, promises to unlock secrets of the universe that have long eluded us. But what if the very discoveries it makes are so extraordinary that they challenge the foundations of our understanding? Imagine peering into the early universe and finding not just the faint glimmers of ancient stars, but objects so bright and enigmatic that they defy current cosmological models. Nobel laureates and leading astronomers are sounding alarms, describing these findings as alarming and unsettling. The implications are profound, suggesting that the universe's infancy may not align with established theories and prompting a re-evaluation of everything we thought we knew about the cosmos. What exactly has the JWT uncovered? How could these seemingly innocuous spots of light challenge the very essence of our scientific theories? As we delve into these questions, we embark on a journey that not only pushes the boundaries of knowledge, but also reveals the ever-evolving nature of science. Join us as we explore the depths of these discoveries, the theories they confront, and the future they promise to unveil. Let's look back at the day the James Webb Space Telescope launched on Christmas Day 2021, and that day that inspiration was delivered. The James Webb Space Telescope was designed and developed by NASA engineers, along with the European and Canadian space agencies. It is the largest optical telescope ever sent into space, weighing in at 6 tons and costing $10 billion. On the morning of December 25, 2021, the Ariane 5 launch vehicle's rockets ignited, causing the ground in French Guiana to tremble. The roar signaled the start of the James Webb Space Telescope's JWST month-long journey to its current home, some 930,000 miles, 1.5 million kilometers, from Earth. Although it took scientists and engineers an additional 5 months to get the 6.5-meter telescope ready for action, the wait was worth it. In the 2 years since its launch, JWST has transformed our view of the universe. It was an achievement 2 decades in the making. But in just a short year since its launch, the James Webb Space Telescope has given scientists new perspectives, amazed the public with awe-inspiring images, and opened our eyes to the infinite possibilities of the universe. Click the follow button now. We're about to uncover an astonishing truth that scientists are calling alarming and concerning. Take a look at this image. This is a newly discovered early galaxy that existed about 13 billion years ago. But researchers found that this galaxy is much larger and more mature than expected for a galaxy in the early universe. This is not the first time that Webb has found such galaxies in the early universe. Since the Webb telescope began its journey, it has challenged our standard cosmological theories. This amazing telescope is not stopping there. This time, the telescope has revealed something disturbing about the universe. Recently, a Nobel Prize-winning scientist revealed that the James Webb Telescope has finally confirmed that our understanding of the universe is completely wrong. Yes, it is not about large and bright galaxies, but this time, some new and more important observations from the James Webb Telescope have shattered long-standing cosmological theories. Consider this. One of the pillars of cosmology is that the spatial distribution of matter in the universe is uniformly isotropic. That is, everything looks the same in every direction if you look over a large enough distance. This is obvious because the forces are expected to act equally across the universe on large scales and therefore do not create any observable inequalities in the large-scale structure during the evolution of the initial matter field created by the Big Bang. Wherever you look, you see the same density of matter, the same temperature, and the universe is expanding the same everywhere. For more than a century, scientists have developed various cosmological models that assume that our universe is uniform in all directions. The Big Bang model, which is the best theory for understanding the universe, is also based on this assumption. The cosmic microwave background radiation also shows that the universe is the same everywhere. But a new study published on February 6 in the astrophysical journal Letters suggests that there may be something really wrong with this assumption. Astronomers have recently confirmed that the rate of expansion of our universe is not the same everywhere in the cosmos. In this paper, they reveal that depending on where we look, the universe is expanding at different rates. Now, this is a big problem because if the universe is expanding at different rates in different places, it would create a big problem for astronomers. This new study also suggests that we may be completely wrong about our current estimates of the age and nature of the universe. We wouldn't call it a tension or a problem, but a crisis, says Nobel Prize-winning astronomer David Gross. Let's dive deeper into this discovery and see how the new Webb telescope discovery confirms a crisis in cosmology. In 1929, Edwin Hubble provided the first observational evidence that our universe is expanding everywhere. Using the largest telescope of the time, he discovered that the farther a galaxy is from us, the faster it appears to be receding into space. This means that the universe is expanding equally in all directions. From this discovery, scientists thought that if the universe is expanding, then this expansion must have started at some point in the past, which means the universe must have a finite age. And since the expansion is happening equally everywhere, by precisely determining the rate of expansion, known as the Hubble constant, the cosmic clock can be rewinded and the age of the universe calculated. But before the Hubble telescope was launched, there was huge uncertainty about the rate at which the universe is expanding, or the Hubble constant, h0. This value is needed to calculate the age of the universe, estimate its evolution over billions of years, and understand the forces that drive it. When the Hubble Space Telescope was launched, it revealed that the universe could be as young as 9.7 billion years or as old as 19.5 billion years. But this younger value posed a big problem. It meant the universe was younger than the oldest known stars. Over the centuries, astronomers have used a variety of methods to measure the exact value of the expansion rate. But surprisingly, each method gives different values. It is as if the universe is expanding differently for different observations. Currently, there are two gold standard methods for finding the Hubble constant. The first method involves sifting through tiny fluctuations in the cosmic microwave background, an ancient relic of the universe's first light, created just 380,000 years after the Big Bang. Between 2009 and 2013, astronomers mapped this microwave blur using the European Space Agency's Planck satellite to infer a Hubble constant of about 67 kilometers per second per megaparsec. In the second method, we use a Cepheid variable star or supernova as a distance source. As Cepheid stars get brighter, they pulsate more slowly, giving astronomers a way to measure their absolute brightness. By comparing this brightness to the observed brightness, we can calculate the rate at which the universe is expanding. But this is where the mystery begins. According to Cepheid variation measurements, the expansion rate of the universe is about 74 kilometers per second per megaparsec, an incredibly high value when compared to Planck's measurements. Initially, some scientists thought that this discrepancy might be the result of measurement error. But recently, Adam Rees, professor of physics and astronomy at Johns Hopkins University, said, "We have now covered the entire range that Hubble observes, and we can rule out measurement error as the cause of Hubble's stress with very high confidence." In addition, new images from the James Webb Space Telescope confirm that previous measurements are correct and that the universe is expanding differently in different places. This difference in the value of the expansion rate of the universe suggests that perhaps the universe is not the same everywhere. Well, if this is true, then our standard cosmological model falls apart because we cannot estimate the age and size of the universe using different values of the expansion rate. And the most important question that arises is, why is the universe expanding differently in different places? One interesting reason could be that dark energy, the mysterious force that seems to be driving the acceleration of the expansion of the universe, is itself not uniform. In other words, dark energy is stronger in some parts of the universe than in others, causing different expansion rates. Scientists claim that if the universe is not homogeneous and isotropic, it means that the laws of physics as we understand them are incomprehensible. Just above the cosmic horizon, gravity could work in reverse. The speed of light could be slower than walking speed, and unicorns could be real. This new discovery from the James Webb telescope has sparked a major debate among astronomers. The reason is that the uneven expansion of the universe challenges the cosmological principle, which is one of the foundations of astronomy. What do you think about the above event? Subscribe to our channel and leave a comment below. We will discuss this issue together. Now, don't take your eyes off the screen. Join us as we explore the amazing things JWT has discovered over the past 2 years. Number 1. Unveiling the Crab Nebula. Within the constellation of Taurus lies the Crab Nebula, a canvas of cosmic activity captured here through Webb's NIRCam and MIRI. The compass on the image may seem inverted because we're used to maps of the Earth, but this is the sky map and we're looking up into it. The scale here is immense, defined by light years. A distance light travels in a year, about 588 trillion miles. The light we see in this image began its journey 6,500 years ago, traversing time and space to reach us. Across this stretch, the image covers 10 light years. At the core of the nebula is a pulsar, the remains of a supernova, spinning rapidly and flashing like a lighthouse. The Crab Nebula, or M1, is not just a remnant, but a birthplace for new elements that make up planets and life. In this 5.5 arc-minute wide snapshot, we're witnessing a part of the universe's continuous cycle of death and rebirth. Isn't it a marvel how destruction and creation are intertwined in the cosmos? Number 2. The Majesty of Max 0416. Gaze at the image of Max 0416, a galaxy cluster so massive that it bends light around it. This cluster has been captured by Hubble in visible light and by Webb's NIRCam and infrared, offering a dual perspective on the same celestial marvel. The compass arrows here might seem backward, but they're not. They simply reflect the sky's orientation from our ground-based point of view. The scale is measured in arc minutes, a sliver of the sky's vast canvas, with the entire image stretching just over 2 arc minutes wide. That's a tiny angle, but it represents an immense portion of the cosmos. Known formally as Max J046.12403, this cluster lies in the constellation Eridanus. It's a gravitational lens, warping space to magnify and distort the light of galaxies behind it. It's like looking through a cosmic magnifying glass, revealing galaxies that would otherwise remain hidden. Such clusters are not just fascinating subjects for images, they're also critical to our understanding of how mass is distributed across the universe. Through Max 0416, we peer deeper into the universe's mysteries. Number 3. Max 0416 and the Marvelous Mothra. Venture into the cosmic depths and feast your eyes on Max 0416, a galaxy cluster with a special twist. This isn't just any cluster. It's a colossal cosmic magnifying glass, bending light across the eons to unveil a spectacular secret. A distant galaxy that flickered into existence a staggering 3 billion years after the Big Bang. And there's a standout star in this galactic ensemble, fondly named Mothra by the scientists, charmed by its brilliance. This isn't your ordinary star. Mothra shines with a light magnified over 4,000 times, a brilliant beacon that has traversed time and space to greet us. But what's the power behind Mothra's extraordinary glow? It's the combined might of Max 0416 and a mysterious lens, a dense celestial body with the mass of a swarm of stars known as a globular cluster. This discovery, nestled in the constellation Eridanus, is not just a testament to the wonders of the universe. It's also a thrilling clue in our cosmic detective story as we unravel the nature of the universe's hidden mass. Each glimmer in the vast dark is a story, and Mothra's is one of ancient light amplified across the ages, reaching us against all odds. What else might lie out there waiting to be magnified into view? The universe is full of such dramatic tales, and Max 0416 is just one chapter. Number 4. Webb's groundbreaking discovery, thorium from a star merger. In a celestial drama of epic proportions, Webb has struck scientific gold, or rather, thorium, detecting this rare element in the cosmos. In the grand tapestry of the universe, 2 neutron stars, remnants of stellar explosions, danced their gravitational tango in a distant galaxy before ultimately merging in a cataclysmic event. The prelude to this discovery began with 2 stars bound by gravity's inexorable pull within a spiral galaxy far beyond our own. Each star met its end in a supernova, leaving behind neutron stars, incredibly dense celestial objects. Propelled by their explosive births, these stars embarked on an intergalactic odyssey, finally colliding after several 100 million years. This violent merger set the stage for a spectacular cosmic light show, a gamma-ray burst, GRB 23307A, an explosion so powerful it shines with the light of 1,000 novas. GRB 23307A, first spotted by the Fermi Gamma-Ray Space Telescope, stands out as the second most luminous gamma-ray burst we've ever seen. Webb's infrared capabilities allowed scientists to pinpoint the origin of these neutron stars and witness the aftermath of their merger. It's here that Webb spotted signs of thorium, an element scarcer than platinum on Earth, within the kilonova glow. This marks the first time such a heavy element has been directly observed in the aftermath of a neutron star collision. The significance? Kilonovas are now confirmed as cosmic forges, where the universe's heavier elements are crafted. Webb's detection of thorium is just the beginning. Astronomers are on the brink of uncovering more secrets of the cosmos, revealing the origins of elements that construct the world around us. This discovery not only enriches our understanding of the cosmic life cycle, but also hints at the untold treasures still hidden in the vast darkness, waiting for Webb to reveal them. Number 5. The distant beacon. Unveiling a primordial black hole. Astronomers have peered across the cosmic expanse to witness a black hole from the universe's dawn. Using the keen eyes of the Chandra and Webb space telescopes, this black hole, detected through its X-ray whispers, holds the record as the most distant one we've ever seen, shining from a galaxy known as UHZ1. Such X-ray emissions are the hallmarks of a supermassive black hole feasting on surrounding material, growing larger with every bite. The black hole's story unfolds against the backdrop of the galaxy cluster Abell 2744, imaged here in infrared by the James Webb Space Telescope. This cluster, nicknamed the Pandora Cluster, is a cosmic crossroads, a gathering of galaxies whose light has traveled for billions of years to reach us. As we dive into Webb's infrared portrait, we find an ocean of darkness sprinkled with distant suns and galaxies. These dots of white, orange, and purple light are not just points, but entire galaxies, each with their own stories spiraling and stretching across the void. Among this cluster of galaxies lies an inconspicuous orange dot, seemingly modest, yet a beacon from the past, signaling from 13.2 billion light-years away. That speck houses a burgeoning supermassive black hole in the galaxy UHZ1, a rare glimpse into the early life of such cosmic giants. This image is not just a photo, it's a window into the early universe, offering clues to how the first supermassive black holes emerged. It's a snapshot of a youthful universe, and within it, a black hole that's grown for billions of years since. It's a profound reminder of the vastness of the universe and the enduring mystery of its origins. Before JWST, astronomers thought galaxies began as small clouds of gas, dust, and stars that gradually grew into the island universes we see today. But the telescope's ability to see infrared radiation allows it to peer farther into space and thus further back in time to when galaxies first formed. JWST has found several of these youngsters that date to within 500 million years of the Big Bang, and they are much brighter than anyone expected. The galaxies could be more efficient at creating stars than predicted, churning out massive stars at a higher rate, or most intriguingly, more massive than astronomers believed possible. Scientists also have found more advanced structures in some spiral galaxies around cosmic noon, when the universe was 2 billion to 3 billion years old and making stars at their greatest rate. In addition to making amazing discoveries, JWST also combines with other telescopes to create stunning images, like this one of the Ghost Galaxy M74. Early supermassive black holes. Astronomers found the most distant black hole ever detected in X-rays in a galaxy dubbed U8Z1 using the Chandra and Webb space telescopes. Everyone knows that black holes grow as they devour passing stars and clouds of gas and dust. So it comes as a surprise to find supermassive black holes, SMBHs, lurking in the early universe when they haven't had much time to chow on their surroundings. JWST has discovered several black holes, weighing about 1 billion solar masses dating to 800 million years after the Big Bang. Perhaps even more importantly, the telescope has turned up much smaller SMBHs with masses from 1 million to tens of millions of suns at even earlier times. This could provide astronomers with enough data to figure out how these behemoths evolve. Dust in the universe's youth. A young galaxy called JADES GS-Z6 was recently targeted with JWST. The powerful telescope noted possible traces of molecules not expected so early in cosmic time. Dust appears all around us, in fluffy bunnies lurking under our beds, in dark clouds blocking our view of the Milky Way, and as signatures in the spectra of distant galaxies. Most dust contains carbon, so it's a relative latecomer to the cosmos because early stars had to forge the element from their initial supplies of hydrogen and helium. Yet, JWST has found dust in a galaxy just 1 billion years after the Big Bang. The dust has a unique chemical fingerprint, suggesting it may be a mix of graphite or diamond-like grains created in the earliest stars. It opens a new window into dust production and galaxy formation. Studying star formation in detail. The Rho Ophiuchi cloud complex, the closest star-forming region to Earth. Stars form in dense clouds of gas and dust. Unfortunately, dust blocks visible light, shielding much of the process from view. But the infrared radiation JWST sees penetrates dust, opening a new window into starbirth. For example, it has revealed thousands of new stars buried deep within the Eagle Nebula, M16, that Hubble couldn't reach. And JWST also showed remarkable detail in a section of the nearby Rho Ophiuchi complex. The telescope's images have revealed dozens of young, low-mass stars, as well as the jets they emit, which light up surrounding clouds of molecular hydrogen. A dusty supernova remnant. At left, supernova remnant Cassiopeia A, CAS-A, as captured by NASA's James Webb Space Telescope's NIRCam, near-infrared camera, and MIRI, mid-infrared instrument. Just 340 years ago, light from an exploding star first reached Earth. Today, we see the supernova's remnant, known as Cassiopeia A, CAS-A, as a 10-light-year-wide debris shell. CAS-A's stunning beauty in the infrared comes from wispy tendrils of gas and the soft glow of warm dust. The dust intrigues astronomers because it is a basic building block of planets and life. They suspect most cosmic dust forms from the heavy elements supernova eject, though previous studies couldn't explain the amount of this material seen in early galaxies. Scientists hope JWST's observations of Cas A and other supernova remnants can shed more light on its creation. A jumbo surprise. The jumbios, short for Jupiter mass binary objects, discovered by the JWST. Deep in the heart of the Orion Nebula, M42, lie at least 40 planet-sized objects with a binary companion. Dubbed jumbos, short for Jupiter mass binary objects, the bodies defy all expectations. Although many stars have companions, astronomers didn't think planetary mass objects could. No star formation theory can create objects this small. And if they develop in circumstellar disks like planets do, they shouldn't be able to survive a forceful ejection. Astronomers likely will need to revise their ideas about star or planet formation or come up with a new theory for creating these jumbos. A molecular exoplanet revolution. This artist's concept shows what exoplanet K2-18b could look like based on science data. It orbits the cool dwarf star K2-18 in the habitable zone and lies 120 light-years from Earth. Although images draw the most attention, spectroscopy plays a huge role in JWST's explorations. It allows astronomers to determine the redshift and thus distance of faraway galaxies, and to analyze the chemical composition of astronomical objects. Nowhere is this more important than in the study of exoplanet atmospheres, where JWST's infrared capabilities allow it to detect molecules invisible in optical light. Among its many discoveries, JWST has found methane, carbon dioxide, and dimethyl sulfide in K2-18b, a rocky world in its star's habitable zone, hinting that it could harbor a water ocean on its surface. Rings around the Ring Nebula. NASA's James Webb Space Telescope has observed the well-known Ring Nebula in unprecedented detail. The Ring Nebula, M57, in Lyra, ranks among the sky's most beautiful planetary nebulae, the end state of sun-like stars. JWST has revealed intricate details in the ring itself, which comprises some 20,000 clumps of molecular hydrogen. But what really sets M57 apart in JWST's images is a series of 10 concentric arcs beyond the main ring's outer edge. Astronomers think the arcs first formed near the dying star when ejected gas interacted with a low-mass companion that orbits at a distance about that between the Sun and Pluto. Diving into protoplanetary disks. These Webb images show a part of the Orion Nebula known as the Orion Bar. The largest image on the left is from Webb's NIRCam, Near-Infrared Camera, instrument. At upper right, the telescope is focused on a smaller area using Webb's MIRI, Mid-Infrared Instrument. At the very center of the MIRI area is a young star system with a protoplanetary disk named D203506. The pullout at the bottom right displays a combined NIRCam and MIRI image of this young system. Planets form in dusty, gaseous disks surrounding young stars. JWST observations not only have provided unprecedented detail in these protoplanetary disks, but also tantalizing clues of precursors to life. Around the nearby star Fomalhaut, the telescope found 3 nested belts of warm dust, suggesting that planets shaped the disk. The observatory also detected water vapor in the inner disk surrounding PDS 70, showing that any terrestrial planets forming there would have access to water. And in the protoplanetary disk surrounding the young star D203506 in the Orion Nebula, JWST discovered the methylcation, a molecule that likely plays a key role in interstellar organic chemistry and the genesis of life. The James Webb Space Telescope has made stunning discoveries, opening up new perspectives on the dark ages of the universe. The images and data captured not only reveal the farthest corners of space, but also the current understanding of the formation and evolution of galaxies and stars. The Nobel laureate has presented the terrifying truth about what the telescope has seen, and it is truly alarming. The existence of ancient cosmic objects, including supergiant universes and previously unknown angels, raises new questions about the origin and development of the universe. This is not only a great step forward for science, but also a reminder of the mysteries that await to be solved in the not-too-distant future. Thank you for watching. Subscribe to our channel to stay updated with fascinating scientific discoveries and the mysteries of the universe. Follow us and join us on this journey of exploration. The James Webb Telescope is a giant leap in the history of stargazing. With its advanced capabilities, including its ability to peer back in time to the very first galaxies that formed after the Big Bang, the Supreme Observatory is expected to shed light on fundamental questions about the origins and evolution of the cosmos. However, more than 2 years after operation, the telescope, albeit solved a lot of puzzles, is raising big questions about the early universe. The data obtained by James Webb isn't just quite what scientists expected. So, though dazzled by Webb's stunning images of deep space, scientists had to admit that something was amiss. What the telescope has revealed contradicts scientists' current theory of how the universe grew up, and it's beginning to look as if we may need to rewrite the history of the cosmos and reshape humanity's position within it. Join us as we dig deep into how exactly James Webb just broke our universe in 2 years. The James Webb Space Telescope, as you know, is one of the most advanced telescopes ever built. Planning for James Webb began over 25 years ago, and construction efforts spanned over a decade. It was launched into space on December 25, 2021, and within a month arrived at its final destination, 930,000 miles away from Earth. Its location in space allows it a relatively unobstructed view of the universe. The telescope design was a global effort led by NASA and intended to push the boundaries of astronomical observation with revolutionary engineering. Its mirror is massive, about 6.5 meters in diameter. That's nearly 3 times the size of the Hubble Space Telescope, which launched in 1990 and is still working today. It's a telescope's mirror that allows it to collect light. Webb's is so big that it can see the faintest and farthest galaxies and stars in the universe. Its state-of-the-art instruments can reveal information about the composition, temperature, and motion of these distant cosmic objects. Thus, for thousands of space scientists, the James Webb Space Telescope is a window to that unknown universe. Just how far back can James Webb peer into the cosmos and into the past? Well, about 13.5 billion years. A telescope does not show stars, galaxies, and exoplanets as they are right now. Instead, astronomers are catching a glimpse of how they were in the past. It takes time for light to travel across space and reach our telescopes. In essence, that means a look into space is also a trip back in time. This is even true for objects that are quite close to us. The light you see from the sun left it about 8 minutes, 20 seconds earlier. That's how long it takes for the sun's light to travel to Earth. You can easily do the math on this. All light, whether sunlight, a flashlight, or a light bulb in your house, travels at almost 300,000 kilometers per second. That's just over 18 million kilometers per minute. The sun is about 150 million kilometers from Earth. That comes out to about 8 minutes, 20 seconds. But the farther away something is, the longer its light takes to reach us. That's why the light we see from Proxima Centauri, the closest star to us aside from our sun, is 4 years old. That is, it's approximately 40 trillion kilometers away from Earth, so that light takes just over 4 years to reach us. Or, as scientists like to say, 4 light years. Most recently, James Webb observed Earendel, one of the farthest stars ever detected. The light that the telescope sees from Arendelle is about 12.9 billion years old. The Webb Space Telescope is looking much farther back in time than previously possible with other telescopes, such as the Hubble Space Telescope. For example, although Hubble can see objects 60,000 times fainter than the human eye is able, the Supreme Observatory can see objects almost 9 times fainter than even Hubble can. But is it possible to see back to the beginning of time? The Big Bang is a term used to define the beginning of our universe as we know it. Scientists believe it occurred about 13.8 billion years ago. It is the most widely accepted theory among physicists to explain the history of our universe. The name is a bit misleading, however, because it suggests that some sort of explosion, like fireworks, created the universe. The Big Bang more closely represents the appearance of rapidly expanding space everywhere in the universe. The environment immediately after the Big Bang was similar to a cosmic fog that covered the universe, making it hard for light to travel beyond it. Eventually, galaxies, stars, and planets started to grow. That's why this era in the universe is called the Cosmic Dark Ages. As the universe continued to expand, the cosmic fog began to rise, and light was eventually able to travel freely through space. In fact, a few satellites have observed the light left by the Big Bang, about 380,000 years after it occurred. These telescopes were built to detect the splotchy leftover glow from the Big Bang, whose light can be tracked in the microwave band. However, even 380,000 years after the Big Bang, there were no stars and galaxies. The universe was still a very dark place. The cosmic dark ages wouldn't end until a few 100 million years later, when the first stars and galaxies began to form. The James Webb Space Telescope was not designed to observe as far back as the Big Bang, but instead to see the period when the first objects in the universe began to form and emit light. Before this time period, there is little light for the James Webb Space Telescope to observe, given the conditions of the early universe and the lack of galaxies and stars. Peering back to the time period close to the Big Bang is not simply a matter of having a larger mirror. Astronomers have already done it using other satellites that observe microwave emission from very soon after the Big Bang. So the James Webb Space Telescope observing the universe a few 100 million years after the Big Bang isn't a limitation of the telescope. Rather, that's actually the telescope's mission. It's a reflection of where in the universe we expect the first light from stars and galaxies to emerge. By studying ancient galaxies, scientists hope to understand the unique conditions of the early universe and gain insight into the processes that helped them flourish. That includes the evolution of supermassive black holes, the life cycle of stars, and what exoplanets, worlds beyond our solar system, are made of. However, data obtained by James Webb isn't quite what scientists expected. In the 2024 Isaac Asimov Memorial Debate, astrophysicist and science communicator Neil deGrasse Tyson moderated a discussion at the American Museum of Natural History in New York. The conversation was between scientists and surrounded the topic of how data from the telescope may be shifting our fundamental understanding of our universe. From discrepancies in the age of the universe to the unexpected brightness of early galaxies, the James Webb Space Telescope has already prompted scientists to reconsider how the early universe once operated, leading to revelations that could trigger major shifts in our models of the universe during the next decade or more of James Webb's tenure. And in the words of panelist Mike Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin, the data from the telescope paints a consistent and consistently new picture of the early universe. The trouble began almost as soon as James Webb first peered into the distant universe. Webb's first views of such distant, ancient regions of space were confusing in two ways. First, some of its images contained huge numbers of galaxies. Far more, in fact, than astronomers thought possible so far back in time. Second, a handful of those galaxies appeared to be monstrously massive. These all dated back to the first 700 million years of the universe. And they were up to 100 times as heavy as scientists thought possible back then. For that reason, these galaxies were dubbed universe breakers. Our current understanding of how the universe grew up goes like this. First, dark matter collapsed into giant clumps known as halos. This happened within the first few 100 million years after the Big Bang. The halo's gravity then pulled in normal matter. This eventually formed stars and galaxies. This would have taken time. Matter would have clumped together slowly, eventually building up larger and larger galaxies. If true, the jumbo galaxies that James Webb spied so soon after the Big Bang shouldn't be possible. What's more, the current story of the universe doesn't predict nearly enough dark matter, halos in the early universe as would be needed to build the many big galaxies that the telescope saw. In that light, things look pretty dire for scientists' current theory of how the universe evolved. The case of the surprisingly active early universe might be related to another well-known discrepancy in astrophysics, the age of the universe. The Hubble Space Telescope was a huge factor in helping narrow down the scientific consensus on the universe's age. In fact, the telescope's mirrors were specifically made to observe stars called Cepheids that astronomers can use to calculate that age. The resulting measurement of the universe's age, about 13.7 billion years, has stood ever since. But let's not forget, there is another way to measure the age of the universe. That's with the cosmic microwave background, the light from the earliest phases of the universe. Using this method, scientists came up with a slightly larger number, 13.8 billion years. And while that difference may not seem huge, some estimates using Cepheids are as low as 12.8 billion years. Worse, no one knows where the difference comes from. It's like we're digging a tunnel on opposite sides of a mountain, and we missed. Unfortunately, the surprisingly luminous early galaxies captured by James Webb did nothing to solve this mystery. In fact, the telescope's results led Rajendra Gupta, an astrophysicist at the University of Ottawa, to publish a paper suggesting that, based on the new data, the universe could be as ancient as 26.8 billion years old, about twice as old as current estimates. While the panelists agreed that Gupta's suggestion is extremely unlikely, the discrepancy of the universe's age in general does suggest the standard cosmological model and our understanding of the impact dark matter and dark energy have on our universe may need some revamping. Put simply, it could be that something fundamental is missing in our current picture. What's notable, the impossible early galaxies aren't even the only things that keep cosmologists up at night. The Webb telescope has double-checked the work of its older sibling, the Hubble Space Telescope. Hubble's measurements of the expansion rate of the universe are exemplary, the trailblazing observatory found, further ratcheting up the so-called Hubble tension. Putting it simply, measurements of the expansion rate of the universe, defined by a property called the Hubble constant, just don't add up. On one hand, observations of the cosmic microwave background radiation, which is like a baby picture of the cosmos from just 379,000 years after the Big Bang, say the universe should be expanding today at a rate of about 67.8 kilometers per second per megaparsec. This means that every volume of space a million parsecs across should be expanding at a rate of 67.8 kilometers every second. An alternative way to measure this expansion is by climbing onto the cosmic distance ladder, where each rung is formed by a different astrophysical milestone such as Cepheid variable stars and Type 1 supernovas. How bright these objects are can tell us their distances, which we can then compare to their redshift values to determine how much the universe has expanded while their light has been traveling to us. However, the problem is, this method gives us a completely different value of the Hubble constant, somewhere around 73.2 kilometers per second per megaparsec. The apparent paradox between the two measurements is what cosmologists have started calling the Hubble tension. Nobody knows what is causing it. but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error on the bottom rung of the cosmic distance ladder, which is home to the Cepheid variables. These are stars with luminosities that predictably fluctuate as the stars pulse in and out. The longer the pulsation period between moments of maximum luminosity, the greater that maximum luminosity is. This period luminosity relation allows us to accurately calculate their distances to Earth. It's possible to measure the pulsation period to calculate maximum luminosity. Then, based on how bright a Cepheid variable appears in the sky to us, we can work out how far away it must be to appear that bright. But it's not quite a foolproof method. The Hubble Space Telescope is able to observe Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, there was a concern that unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheids' apparent brightness values, creating an unseen and systematic error in the measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our vantage point on Earth. But new measurements achieved with the James Webb Space Telescope of 5 galaxies hosting a combined total of more than 1,000 Cepheid variables have ruled this possible error out. James Webb's infrared vision is able to cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables so they stand out from the crowd. The 5 galaxies observed by James Webb, the most distant of which is NGC 5468, at 130 million light-years from us, have also hosted a combined total of 8 Type Ia supernovas over recent decades. These supernovas, which signal the destruction of white dwarfs, have a standardizable luminosity curve and form the next rung on the cosmic distance ladder above Cepheids. Because the preceding rung is required to calibrate the next rung, Webb's observations of Cepheid variables therefore makes the distance measurements using Type 1 a supernovae, which are bright enough to be seen in much more distant galaxies than Cepheids, more accurate. And they too tell us that there is a contradiction in the different measurements of the Hubble constant. From these Webb's measurements, astronomers led by Adam Rees of Johns Hopkins University determined that Hubble's original measurements were spot on. In the words of Rees, we've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. What remains is the real and exciting possibility we have misunderstood the universe. We need to find out if we are missing something on how to connect the beginning of the universe and the present day. In other words, the tension at the heart of cosmology is here to stay. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution that would have implications far beyond the world of science. After all, there is no question that we have made incredible progress in understanding our universe, its history, and its origin. But it is also undeniable that we are profoundly puzzled, especially when it comes to the earliest moments of cosmic history. We have no doubt that these moments hold incredible secrets and perhaps the keys to a new scientific revolution. But our universe holds its secrets closely. It is up to us to coax those secrets from its grip, transforming them from mystery into discovery. In a recent remarkable finding, James Webb has discovered that early universe galaxies must have grown up way faster than expected. Plus, the same team also found that 10 billion years ago, the cosmos wasn't quite as disordered and chaotic as previously believed. The international team, led by researchers from Durham University in the UK, reached these conclusions by discovering evidence of structures called star bars, forming in galaxies that existed just a few billion years after the Big Bang. Star bars are elongated regions of increased star density found at the hearts of spiral galaxies like the Milky Way and other disk galaxies. As they form, star bars push gas toward the hearts of their respective galaxies, thereby regulating starbirth. The presence of these central bar structures thus indicate that a galaxy has entered a more settled and mature phase. As Zoe LeConte, team leader and a researcher at Durham University, said in a statement, "Galaxies in the early universe are maturing much faster than we thought. This is a real surprise because you would expect the universe at that stage to be very turbulent, with lots of collisions between galaxies and a lot of gas that hasn't yet transformed into stars. However, thanks to the James Webb Space Telescope, we are seeing a lot of these bars much earlier in the life of the universe, which means that galaxies were at a more settled stage in their evolution than previously thought. This means we will have to adjust our views on early galaxy evolution. Notably, this isn't the first time scientists have gone bar hopping in the early history of the 13.8 billion year history of the universe. The Hubble Space Telescope witnessed these features as well, but that orbiting eye on the universe could only go as far back as 8 billion to 9 billion years. However, the increased sensitivity and wavelength range of James Webb has stretched such observations back at least another 1 billion years. This has revealed bar formation in galaxies that are seen as they were between 8 billion and 11.5 billion years ago. In fact, of 368 disk galaxies the team considered for the study, 20% already had bars. That is double the number observed by Hubble. The further back in time the team looked with James Webb, the fewer bar structures they observed in galaxies. They believe this could be because galaxies at earlier stages of the universe were not as well formed. An alternative may be that shorter bars were more common in progressively earlier galaxies. Even the impressive observational power of James Webb isn't sufficient to see these short bars in early galaxies. With these results in hand, the team now wants to use the telescope to peer even further back into cosmic time, looking back as far as 12.2 billion years ago. This could reveal whether bar growth was common just 1.6 billion years after the Big Bang. As Gadati concluded, the simulations of the universe now need to be scrutinized to see if we get the same results as the observations we've made with the James Webb Space Telescope. We have to think outside of what we thought we knew. In another observation, the Webb telescope has discovered the oldest dead galaxy ever seen. But the cosmic corpse has left scientists puzzled as it defies explanation by our current knowledge of the early cosmos. The galaxy suddenly and mysteriously halted star formation when the universe was just 700 million years old, when countless stars were birthing thanks to an abundance of pristine gas and dust elsewhere in the universe. The galaxy, named JADES GS Z701QU, and described in a paper published in the journal Nature, provides astronomers with a peek into the elusive underpinnings of galaxy evolution in a primordial universe, including why galaxies stop forming new stars and whether forces driving their starbursts alter across epochs. In the words of study lead author Tobias Lusser, a researcher at the University of Cambridge's Kavli Institute for Cosmology, Cambridge or KICC, galaxies need a rich supply of gas to form new stars, and the early universe was like an all-you-can-eat buffet. Current models cannot explain how the newfound galaxy not only took shape in less than 1 billion years after the Big Bang, but also shut down its star factory so quickly. According to study co-author Francesco Diogenio, also a researcher at KICC, it's only later in the universe that we usually start to see galaxies stop forming stars. In comparison, a handful of other dead galaxies found elsewhere appear to have paused forming new stars when the universe was about 3 billion years old. To discover Jade's GS Z7 EWAOQ, Lucer and his colleagues used James Webb's powerful infrared vision to peer through the thick veil of dust obscuring the earliest objects in the universe. In addition to being the oldest dead or quenched galaxy spotted so far, the newfound galaxy is also many times lighter than other similarly quiescent galaxies previously found in the early universe. Webb's data suggest the galaxy intensely formed stars for somewhere between 30 million to 90 million years before it rapidly shut off, although precisely what ended it is still unknown. Astronomers know of a couple different factors that can slow down or extinguish star formation. For instance, turbulence inside a galaxy, such as radiation emitted by a supermassive black hole, can push gas out of the galaxy and starve it of the gas reservoir it relies on to form stars. Another intriguing possibility is that the galaxy's surroundings at the time did not sufficiently replenish the gas reservoir being consumed by birthing stars, leading to a deficit in star-forming material. However, in the words of study co-author Roberto Maiolino, an astrophysicist at KICC, we're not sure if any of those scenarios can explain what we've now seen with Webb. Current models based on the modern universe are unable to explain the properties of JADE's GS Z7901QU, suggesting they may need to be revisited. Another possible explanation for the new galaxy's dormancy could be that galaxies in the early universe die and then burst back to life. However, previous research of dead galaxies from when the universe was around 3 billion years old, a time of its most prolific star birth, suggested such dead galaxies cannot rejuvenate even via mergers with nearby galaxies, which instead only serve to puff them up. As Eugenio said, we'll need more observations to help us figure that out. A quick note, James Webb now is digging deep into the mysteries of gas planets. More specifically, the researchers say they've started making headway in answering the question of how long gas giants likely have to form around their host stars before all the gas around those stars fades away. The short answer is not very long, but the full story is far more nuanced. The research team used the Webb telescope to probe what's a little confusingly known as the disk wind. This doesn't really refer to a wind like you may imagine. Rather, it refers to the process of gas leaving a disk around a star. This disk would be one filled with different types of material with the potential to give rise to planets. It's thus otherwise known as a protoplanetary disk. According to Naman Bajaj, lead author of the new disk wind analysis and a scientist with the University of Arizona's Lunar and Planetary Science Laboratory, we knew that they exist and that they might play an important role in disk evolution. What we didn't know was the underlying physics, and consequently, how much mass is being lost. These are key to answering all our questions on its impact. Such a disk would include non-gaseous debris too, to be clear, like dust that can come together over time to create rocky planets. That's actually how Earth is believed to have formed once upon a time. Though Bajaj and fellow researchers didn't come up with a final, tightly confirmed answer as to how long gas planets may have to form before protoplanetary disk gas depletes fully, he did offer a ballpark based on his calculations. According to Bajaj, considering the gas mass in this disk, and assuming that the gas will keep leaving at this constant rate that we find, about 1 moon mass every year, it will take approximately 100,000 years. Yes, that sounds like a long time. But, as Bajaj emphasized, it's an incredibly short timescale in astronomical terms. A protoplanetary disk lives for about 5 to 10 million years. After all, though it's severely cliché to say at this point, all of this is a testament to how much the James Webb Space Telescope is revolutionizing our understanding of the universe. Its infrared sensitivity is immense for sure, but a lot of its discoveries owe themselves to the body of work already available to build on. The library of papers that's been helping scientists decide where, precisely, James Webb should look.